Can statistics tell you exactly when the next phone call will arrive? No, but it can answer a much more useful question. How many calls are likely to arrive in the next hour? That single question leads us to one of the most useful probability distributions in statistics, the Poisson distribution. Let's compare what we've learned so far. Bernoulli asked, did one event succeed? Binomial asked, how many successes happened after several trials? Poisson asks something completely different. Instead of repeating experiments, it counts how many events happen in a fixed interval. That interval might be 1 minute, 1 hour, 1 kilometer, or even 1 web page visit. Poisson distributions appear whenever we're counting events. How many customers arrived this hour? How many emails arrived today? How many cars passed this checkpoint? How many meteor sightings happened tonight? Notice the pattern. We're never asking when the next event happens. We're asking how many happened during a certain period. Here's something interesting. The events don't happen at regular intervals. Sometimes nothing happens for a long time. Sometimes 2 events happen almost together. The exact timing is unpredictable, but the average number of events stays surprisingly consistent. The exact timing changes. The average rate stays roughly the same. Every probability distribution has an important parameter. For the Poisson distribution, it's the Greek letter lambda. Lambda simply means the average number of events expected during one interval. If a website usually gets 20 errors per hour, then lambda equals 20. If a hospital usually receives 8 emergency patients every hour, then lambda equals 8. Lambda is simply the average event rate. Suppose the average number of calls is 3 per hour. Could we receive 0 calls? Yes. 1? Yes. 2? Of course. 3? Absolutely. 4? Also possible. Every outcome has a probability, but notice something, they're not equally likely. The most likely outcomes appear close to the average. As we move farther away, the probabilities become smaller. So why is 3 the tallest bar? Remember, lambda is the average number of events. If a call center usually receives 3 calls every hour, then getting 3 calls should happen more often than getting 0 or 10. That's exactly what the graph is showing. Watch what happens when lambda changes. As the average increases, the entire distribution shifts with it. Lambda doesn't just change one probability, it changes the whole distribution. Don't memorize this formula, let's understand it. Lambda is the average number of events. X is the number of events we want. P of x equals x is the probability of exactly x events. Suppose a call center receives an average of 3 calls every hour. What's the probability of getting exactly 5 calls? That's all the Poisson formula is doing. It converts the average event rate into the probability of any specific outcome. A website receives an average of 2 server errors per hour. What's the most likely number of errors in 1 hour? Let's answer this without calculating anything. If the average number of errors is 2, what result should we expect most often? The tallest bar appears near the average, so the most likely number of server errors is 2. Sometimes you'll get 1, sometimes 3, occasionally 0, rarely 6 or 7. That's exactly what a Poisson distribution predicts. A Poisson distribution is useful whenever you're counting random events inside a fixed interval. Time, distance, area, volume. Number of emails arriving this hour? Yes. Number of earthquakes this month? Yes. Number of typing mistakes on one page? Yes. Height of a student? No, that's a continuous measurement, and it belongs to a completely different distribution. Where does this appear in AI? Quite often. Cloud systems use Poisson models to estimate server requests, network traffic, hardware failures, and anomaly detection. If a server suddenly receives far more events than expected, an AI system can recognize that something unusual is happening. Poisson isn't just statistics. It's one of the tools that helps keep modern systems running reliably. Let's summarize. Poisson counts events. Events happen during a fixed interval. Lambda is the average event rate. Outcomes close to lambda are usually the most likely, and outcomes far away become increasingly rare. A hospital receives an average of 8 emergency patients per hour. What is lambda? Lambda equals 8. Which situation should use a Poisson distribution? Student height or number of phone calls per hour? The answer is number of phone calls per hour. True or false? A Poisson distribution counts events over a fixed interval? True. Remember it like this. Average rate becomes lambda. Events happen over a fixed interval. We count those events. That's the Poisson distribution. Here's something incredible. As lambda becomes larger and larger, the Poisson distribution slowly starts looking like the normal distribution. Why? That's exactly what we'll explore in the next chapter of our statistics journey.